Hello, here we are going to discuss the solution of these questions which was held in the December. Okay, so for the subject name is digital logic design. It is useful for the digital electronics students also. So here questions are convert the binary numbers 11011 to decimal equivalent. So like this we have objective questions, 1 marks each. Then we have long questions. So we'll discuss quickly the answers so that you can match how much you are correct. Okay. So you can check your answer. Many answers you'll able to remember how you have done your process. So now here, if you see that the first question is to convert this binary number into decimal. So for that, this binary is the weighted codes. That's why we're writing here 0, 1, 2, 3, 4. After that, we are trying to expand. Whenever you are trying to expand any number with their radix, it is going to give the decimal equivalent. So here radix is 2. So we have 1 into 2 to the power 4, 1 into 2 to the power 3. This 0 is not taken since we multiply 0 with 2 to the power 2. That value is going to be 0. So finally here, there is 16, 8, 2, 1. That is 27. Many students, they have written 26 also. Okay. So they have done the mistakes here, might they are confused here. Okay, that this one they have written as the 0. Next we have universal gates. Name the two types of the universal gates. So that is what NAND and NOR gates. Since we are able to design other gates with the help of NAND and NOR gates, but still people have done mistake in this. Advantage of Quine McCluskey methods. So it is very systematic and algorithmic approach. So where we have high variables means when number of variables are more in the K map, then it is a advantage to use that McCluskey method. That is also known as the tabulation method. Minimum number of the cells need to recombine to remove the three literals in case of four variables. So when we have four variables, so in case of four variables, we have four literals are there. So how to make the combination that will get only one literal. So when we have combination of the 8 adjacent boxes, so in this what we'll see that row wise you will not get anything common. Only common wise you will get one literal as the common. So that's why we'll get this expression for this combination by using single literal. So we are able to eliminate three literals. So here answer is 8. Next, full header, how we are going to design with the help of half header and OR gates. So for that we require two half header and one OR gate is required. So next we have to write this borrow in case of full subtractors. So that is given as a dash b plus a dash plus b and overall multiplied with c in. Or this one you can also have written like a dash b plus a dash c in plus b c in. So that is correct. If somebody has written c also means okay. Okay, that is also correct. Next what we have. Next, they are asking the difference between the latch and flip-flop. Many times you have heard, many times it was discussed. So latch is what? Level trigger. L for latch, okay? L for level. So latch is the level trigger device, whereas flip-flop is the edge trigger device. Still people do the mistakes. Now, how many clock pulses are required to shift the 4-bit word into the shift registers? Into 4-bit shift register means for that 4 clock pulse is required. So here, suppose we have 4 shift registers, so that is here. So when we'll apply the first clock, okay, like here, suppose 1, 2, 3, 4 bits are there. So during the first clock, this first bit will be loaded here. During the second clock, okay, the output of the first will be transferred to the second, and here new bit will be loaded. During the third clock pulse, now output of this second flip-flop will be transferred to the third one. Okay. And finally, this third bit will be loaded here. And again, this first flip-flop output will be transferred to the second one. And during the fourth one, this is the output of the third will be given to the fourth one, and second is given to third one, first one is given to second, and here new will be loaded. So like this, 4 clock pulses is required. Next is the difference between SRAM and DRAM. S is the static RAM and D is the dynamic. So in case of SRAM, use the latch, and here DRAM use the capacitor for the storage purpose. SRAM is the fast, DRAM is the slow. And many people have done the mistake in the full form of the EEPROM. So this is electrically erasable, programmable, read-only memory. So this type of the silly mistakes are being done. Next, we have long questions. So these questions carry the 10 marks. So here, these questions are like first question is what? Perform the following number base conversion. So this number is given in the decimal. You have to convert into binary and hexadecimal. So that we are going to find here. So here, this decimal number having integer part as well as decimal parts. So whenever we have to convert this integer part means we are going to divide with radix and corresponding remainder we have to write. So this remainder we are writing in this order. And for the decimal parts, for the fraction, we are going to multiply with concerned radix. So here radix is 2. So after multiplying, what is the integer that we are writing aside? Again, what is the new fraction that is being multiplied with the radix? And here we are writing this integer in this format. Okay, up to down approach. So we'll have 0.101. So finally we'll mix both. So this is the answer here. Now, once we have binary, so this one easily we can convert into the hexadecimal, octal, whatever is required. Okay, so here we are going to use the direct conversion. So now the given decimal number is already converted into binary. So now what is the rule? You have to make the combination of 4 in case of hexadecimals. Okay, you have to make the combination of 4. Why means to the power 4 is what? 16. That's why 4 bits are required. So from here, from decimal left side, from decimal right side, you have to make the combination. Okay. So finally, this is the 1, this is 0, this is the 11 that is equal to B in hexadecimal, and this is the 10 that is equivalent to A. So that's why answer is 10B decimal A. Next, we have they're asking to write some postulates as well as we have to prove this given identity. For that, this important postulates, especially what we are going to use there, that is A plus A dash is a 1. Okay, that is being used here, as well as distributive properties also being used. So like this, we have to use that concept to find the appropriate result. So now here in this, if you see that what we have used, 1 plus A plus A dash is 1. 1 plus we have used 1 plus A is 1. This is the OR gate. Okay. So like this, we are able to simplify this. So which literals are missing that can be multiplied? Okay. Or here, what is the common that we can take as the common? So here in BC, what is missing? A is not there. So we have multiplied with A plus A dash, that is equal to 1. Then we have expanded this one. Okay. Finally, if you rearrange this one, here we have common AB and here we have common A dash C. So A plus C is what? 1. 1 plus B is what? 1. Okay. 1 plus C, since it is the OR gate. So any one input is high, output will be always high. On the basis of this, we are able to obtain. Next question is very important. They always used to ask, that is about this define the Hamming code for the error detection and correction. So first we have to go for the general discussion how Hamming code is useful for the error detection and correction, 1-bit correction. Then here 4-bit information is given 1011. So by using this message by data, we have to generate the 7-bit even parity Hamming code. So clearly here that's given that we have to use the which one? Even parity we are going to use here. So this one we can have some discussion about. Okay. So Hamming code is what? It is used to detect error and it will correct only 1 bit of the errors. So here, if you see that message bits are given. So this message bits, you can write from left to right or right to left, any one pattern you should follow. Okay. But as per the standard way, we are writing from left to right. So number of the how many parity bits will be there for that formula is to the power p minus 1 greater equal to p plus n. So on the basis of that, we are finding p equal to 3 or anyhow, they are given only generate the 7 bits. So 4 messages, so 3 parity bits. Next, we have to decide what are the position of the parity bits. So since we have 3 parity bits, so 0, 1, 2. So finally, to the power 0 is 1, to the power 1 is 2, to the power 2, 4. On the basis of that, we have position of the parity bit, first position, second position, fourth position. So follow either left to right or right to left. Okay. So now we got the position of the parity bits and remaining are the position of the message bits that is being written here. Now it is important that we need to find the values. What are the values of the parity bits? Okay, that is important here. So for that, we are going to use the XOR gate. So it is given here even parity. So when number of ones are even, this parity bit value will be 0 for that combination. If number of ones are not even, then parity bit value will be 1. Since you know that XOR gate is used to represent this odd function, right? Okay. So that's why we are going to use here XOR gates. So that we have to consider the bit position, third, fifth, seven. For P2, third, six, seven. So here what is logic? 1, 3. 1 gap is here. First parity bit we are finding, 1 gap is there. Second parity bits start at 2, 3. Again, 2 gaps are there. Fourth position P4. So 4 consecutive numbers we are going to check bit position 4, 5, 6, 7. Again, gap will be there if bits are available. On the basis of that, parity bits values are P1 is 0, P2 is 1, and P4 is 0. So now this value we have substituted means this is this information is being generated with the help of concept of even parity. Now if you have to detect whether error is going to occur or not, or the received information having error or not, for that again we are going to use the correction bits. For that again XOR we are using here, and what are the bit position we have to check. You see that first position, third, fifth, seventh. So it is same here as before here, just one. What is the position of the parity bit that is being included here? On the basis of that, to detect the error, we have to check the C4, C2, C1 in this order. Okay. If what is the value of this combination, suppose for example, here it is 1. This is the, suppose 0. This is the 0. So finally what is happening here? This one will write 0, 0, 1. So this 0, 0, 1 equivalent is what? 1. That means first bit having error. If first bit having error due to presence of 0, then 0 will change into 1. If it has error due to presence of 1, then 1 will change to the 0. So like this, Hamming code is used to correct the 1 bit of the error. So many people have done mistake in this also. Next, very important McCluskey methods. Okay, that is also called as the tabulation methods. So for that here, what they're asking, find the minimal sum of products expression for the following function by using Q.No McCluskey method, or also known as tabulation method. So here we have 4 variables for that mean terms are given. And these mean terms are given without don't care. Okay. So don't care conditions are not given. So that is also, it's going to become easy. So finally, now in this situation, if you see that what will be the solution we are going to see. So in this, what is the logic? First of all, the given mean terms we have to arrange on the basis of number of ones. So first mean term is 0. So that's why here it is written first one. After that, we have to look the mean terms which having number of ones as the one only. So on the basis of number of ones, they are made in the group, which having same number of ones, they are kept in the same group. So like this, we are going to rearrange. Okay. After that, we have to make the pairing of group 1 with group 0 with group 1, group 1 with group 2, group 2 with group 3, and group 3 with group 4. So what is the condition for that? When we are going to compare two consecutive group midterms, only one literal should change. Then only we'll make the pair. Otherwise, we will not make the pair. That pair will be that particular pair is not going to exist. So after making the pair, again we have to look for the quad. So here you see that pair is made. So at which position bit is going to change, that you can put the dash or underscore. On the basis of that, we have pair table. Again, we are going to compare one pair with another pair group. So if again only one bit is going to change, so then again we'll make the quad. So here, so easy way, first we have to check the at which position we have dash, whether both having dash at the same position or not. If it is at same position, then we'll look for the other elements. Like in case of 0, 2 here, if you see that, and you look for 8, 10. So it having dash at same place. So now we look for another bit. So here A is changing. So that here now in the next quad, in place of A, below A, it will become the dash or underscore. So on the basis of this, we used to make the quad here. Once we'll make the quad, now if you see that octet is possible, we'll go for the octet. But here if you see that, and in this pair or combinations of quad, if same mean terms we are going to get, then that will write only one time. So now finally octet is not possible. So this after that we'll have to go for the prime implicants. So in the prime implicants table, we are going to verify that whether all mean terms are covered or not. So like by using B dash D dash, where we have 0, that is written as the dash, where we have 1, that is written as without complement. So on the basis of this here, we are marking that whether what are the mean terms are covered by these implicants. Again for AC. So finally what you see that this one is not covered, okay, by any of these two. So now we'll look for back to the previous table where mean term 1 was available. So for that we have combination. For that we have littles here A dash, B dash, C dash. So by this mean term 1 is also covered. So finally this is the final answer in terms of sum of product. So this question is attempted by maximum people, but still 80% people didn't reach to the last stage. Next question is about implement the Boolean function by using NAND two-level implementation or NOR. So by using universal gates, we have to implement. So here this given Boolean function, first you can arrange with the normal way by using the AND gate, OR gate, whatever things are required. After that, this AND will be converted into the NAND. So when suppose for example, here we have AND, this one we have convert into NAND. So what we'll do here, here we'll put the bubbles as well as you can attach one inverter, okay, to compensate this. Whereas if whenever we have OR gate, so if this OR gate we are going to convert into NAND gates, so here what we are doing, we are applying the bubbles here at the inputs. Okay, so when bubble is applied at the input, here also we can add the inverter. So if number of inverters are even on the same line, then both will be cancelled. Okay, so like that logic we are going to use. So finally it will become the NAND gates, and here if inverter is required, we'll keep on the particular line if we don't have even number of inverter. So on the basis of that here, it is written. So when we have this some case of the single literals, so that literal is here coming as the complement that you can verify also step by steps. Similarly, next is the by using the NOR gates. So similar logic we are going to use what we are doing there with the NAND gates. So how we used to change AND there, that operation will takes place here for the OR gates, and what we are doing there for the OR gate, that will do here for the AND gates. So that is the basic concept behind this. So next question we have design 8x1 multiplexers using basic gates, and we have to drive the truth table, logic diagram, and selection lines are also they are restricted. We have to use S0, S1, S2. Okay, so input the output. So in this, many peoples they have done a start in well way, but they have drawn the truth table of the decoder also. And many people, what they have done the mistakes, they have not given the data input here. Data input is missing, but they have connected the selection lines. That is the main mistakes. So here, multiplexer, what is given? We have to design the 8x1 multiplexer. So this one we can write to the power 3x1 means 3 selection lines are required. So with the help of 3 selection lines, so we have total 8 combinations are there. So total 8 combinations are written. So when selection lines are 0, 0, 0, output will be Y. What will be the output? I naught. Similarly, when all selection lines are high, output will be what? I7. But this I7 should be given as the input. Then only we'll get the output. Okay. So that is important here. Now if you see this logic diagram of this here. So now here one compulsory input, this is the data input. After that selection line, first one is what? S is 0. S1 is also 0 and S2 is also 0. Okay. So now here this AND gates, all inputs are going to become high. Then output will be also high. So finally this output is going to pass to the OR gates, and OR gate will give the output. If any input is high, it will give the output also high. So similarly for the I naught, what we have combination here. So that combination is what? 0, 0, 1. So 1 is here as 0 is here 1, how we have written there in the truth table. So again, this is the remaining are the 0. So this will come from here. Okay. So this S1 is the 0 here, and this S2 is still 0. So in the similar way, we have to give the connection for the I2. 2 is here. So what is the combination? 0, 1, 0. So like this logic you can use. So S0 is what? 0. S1 will be without complement. Again, S2 is what? With complement. Similarly for I3, what is combination? 3 is 0, 1, 1. So now S0 without complement, S1 also without complement, and S2 will be with complement. Okay. So like this I4 is what? 1, 0, 0. So what will happen here? S0 with complement. S1 also with complement. S2 will be without complement. I5 101. So that means S0 is what? Without complement. S1 is with complement. Okay. So like this, we have to go for the all other combinations. And this one is what? 1. This is also without complement. So similarly, I6 110, I7 111. So 111 is all without complement. Okay. So this is also without complement. In case of 110, what was here? This is S0 is with complement. Remaining two are without complement. Okay, so now you can understand what mistake you have done. And here enable input, all these things are not required. In place of enable filter, if you have given this data inputs means you have some people, few percentage of people have done the proper way. Some of them have given input here like a small inputs. Okay. So this is the multiplexer, it's not decoder. Okay. So that you have to keep in mind. On the basis of that, you need to design. Next, this is the question. 13B is what question? Very easy. We have to design the 4-bit binary adder subtractor. So same circuit is going to act as the adder as well as subtractor. So we have to use 4 full adder and XOR gates, and we have to explain the operation when m equal to 0 addition, when m equal to 1 subtraction. So this one very easy, but less number of people have attempted that. So here if you see that here, what is the logic for this? When m equal to 0, why it's performed the subtraction means, you know about this m equal to 0 means addition, m equal to 1 means subtraction. So when m equal to 0, so now each XOR gate having one of the input is the m, so that is going to become 0. Another inputs are the, in case of addition, this A will be called as the augment, B will be called as the addend. Okay. So in that case, in case of XOR gate, we know that B XOR 0, it will be always B. So that here output we are going to obtain B. So finally full adder is going to perform the simple addition A0 plus B0. So similarly all full adder will do the same operation, and initial carry is going to be 0 here since C0 is same as the M, so it will perform the addition. Whereas in case of M equal to 1, so this subtraction can be done with the help of addition, so where we are going to use the complements. So when we are subtracting, suppose A minus B, so A is called as minuend, B is called as the subtrahend. So now for subtrahend, we are going to take the 2's complement. So when m is 1, each XOR gate having one input as the 1. Suppose here one input is 1 and it is the B1. So now by the XOR gate, we know that B XOR 1 is always B complement, means output depends upon the B. So here we'll get the 1's complement. And already 1 is being added from the previous stage. So 1 will be added. So B dash plus 1, it is going to give us the 2's complement of the subtrahend. So like this, we are able to perform the subtraction with the help of addition. And finally, this XOR gate is going to check the overflow conditions. So it is the easy to draw the diagram as well as explanation for the binary subtraction and addition. So next we'll see the next questions. So next question is about describe the operation of JK flip-flop, including the logic diagram. And second part of this is the explain the concept of propagation delay in case of 4-bit ripple count, and calculate the maximum clock frequency if each flip-flop has a delay of 10 nanosecond. Okay, on the basis of that, next solution we are going to see. So first we need to explain the JK flip-flop. So JK flip-flop, you know that here in the operation of this JK flip-flop, you can design with the help of D flip-flop in this way. So since D flip-flop is economical, so maximum flip-flop we are trying to design with the help of D flip-flop. So now here this Q bar is one of the input to the JK flip-flop. Since here in general, if you have a conversion table in your mind, so this D expression is going to become J Q dash plus K dash Q. So on the basis of that here, one AND gate is required. So that input is J, another is the Q bar or Q dash. Another AND gate, what is the input? K dash. So inverter is required here, and it is another input is the Q. And finally, it is given to OR gate to make the sum of this. So this is the OR gate, and OR gate output is given to the input to the D flip flop. And here, if you see the truth table, so when we have both inputs are 0, 0, then no change. So next state is the same as the present state. So there will be no change. Okay, if Qn is 0, Qn plus 1 also will be 0. 0, 1. When combination is 0, 1, it will be the reset. Okay, so here Qn plus 1 next state is going to be the 0, and Qn plus 1 dash will become the 1. So when we have 1, 0 set and 1, 1 means this is going to be complement. Okay, so keep on changing. If Qn is 0, Qn plus 1 will become 1. If Qn is 1, Qn plus 1 will become 0. So it is going to toggle each other. Okay, so it is always we are going to get the complemented outputs. So this was the problem in case of SR flip-flop when both inputs are 1. So that we overcome here in case of JK flip-flop. So later we have discussion about race around condition also. Now, second part of this, what they're asking here, propagation delay is given for the one flip-flop. So now the total propagation delay is given as 4 into the delay of the each flip-flop. Here we have 4-bit ripple counters. So 4 flip-flops are required. So it is multiplied by 4 and delay of one flip-flop. So finally total delay is 4 into 10 nanoseconds. That is the 40 nanoseconds. And time period is the inverse of the frequency. So f equal to 1 by t. On the basis of that, it is calculated. So finally, we have 25 megahertz maximum clock frequency. Okay. So these are not difficult, but still people have not answered properly. Next question we have 14b. That question is compare ring counter and Johnson counter. Draw the logic diagram for 4-bit ring counter and leads is 4-bit 4-state sequence. So we have to use the 4-state sequence. They're talking means we have to use the 4 flip-flops here. So now in this discussion, if you see that first is the difference between ring counter and Johnson. So ring counter and Johnson counter both are the example of the synchronous counter that you know. So here in case of ring counter, number of unique states are 4. In case of Johnson, we have 8. And unused states are more in case of ring counter, that is to the power n minus n. Whereas unused states in the Johnson is to the power n minus 2n. So this is the basic difference how Johnson counter is going to take advantage over the ring counter. So now here we have discussion about the ring counter. So it is the example of the synchronous. So each flip-flop. So it is given that we have to design 4-bit. So 4 flip-flops are required. So each flip-flop is given the same clock pulse since it is the example of the synchronous. Okay. Synchronous counter. So here output of last one, that is Q, is connected back to the input to the first flip-flop. Okay. Whereas in case of Johnson counter, Q dash is connected back to the input. So many students, they confused. Some of them connected Q dash also in case of ring counters, and some of them have not given the clock pulse. So here again, input also we are given from the output of the last one given input to the first one, and from each stage we have to obtain the output. So now if you see this sequence, how it is going to generate and how it has 4 states, 4 unique sequence. So for that here, if you are taking the initial clock pulse, in that if combination is 1, 0, 0, 0, this is output of the flip-flops. Now this Q0 is given input to the previous one. So finally this is coming here. Okay. This 0 will come here and remaining are going to shift. So this is shifted here. This is shifted here. This is shifted. Again, that last 0, what is the Q0 last flip-flop, rightmost flip-flop output, that is going to become input here to the first flip-flop. Again, it is being shifted. Okay. So like this, what you are saying that after 4 clock pulse, same states we are going to obtain. So that's why it has only 4 unique states here. Okay. So that is represented here. As if they're asking timing waveform, then you can draw the timing waveform. Okay. If it is not required here, but if you have drawn also means okay, fine. So next question is about implement the following two Boolean function using the programmable logic array with 3 inputs. It's important here. 3 inputs, 4 product terms, and 2 outputs. So here maximum students, 90% students, they have done the mistakes. First of all, it is the programmable logic array means AND array and OR array both are programmable. And main point is that here they're talking about 4 product terms, means 4 unique product terms we have to obtain. Okay, so that we are going to see in the solution how we'll have 4 unique product terms. Okay, then you'll understand your mistake. So now in this, whatever function is given, for that first we need to go for K-map. So here we have 3 variables. So 8 boxes are required. So we have gone for the K-map. So here if you see that if you make the combination of the given mean terms for the both the function, then we'll not get 4 unique products. Okay, so that's why complement of one function is taken. For here, complement of f1 is taken, okay, and f2 is taken as it is. So finally, complement means which mean terms are not given. For that, we need to write the 0 and we have to make the combination of those zeros only. So here f1 dash is AC plus BC plus AB. Again, you know that complement of the complement will give the same thing. So that's why complement is taken here. So it is f1 equal to AC plus BC plus AB dash. And here f2 in the normal way combination we have same. So now here what you see that AC is common. Next what is common? AB is common. So 2 product terms are same. Okay, in both. Then this is third one and this is the fourth one. So now we are able to obtain the 4 unique product term. That is important. If suppose you are fortunate by direct taking the K-map in the sum function, you will get 4 product term, means no need to go for the complement. But here you must have to take the complements, otherwise you will not get the 4 unique product terms. So once we'll get the 4 unique product terms, then we have to draw the logic diagram. So in this logic diagram, we are going to use the concept of logic array. Okay, so that's why we have drawn like this. And this one, now if you see that one is going to represent f1 dash, another is f2. Now it is important here to use the XOR gate. At the output, we need to use the XOR gates. So many people have tried, but 90% people have done mistake in this. So the XOR gate, what is the concept that X XOR 0 is X. So F2 is given here input as the 0. Second input, X XOR 1 is X dash. That's why this F1 dash is given, another input is what here? 1. So finally we have F1 and F2. So this section is required here. XOR gate is required. And here 2 functions are there. So 2 OR gates are required. And we have 4 unique product terms. That is important here. Okay, so remaining inputs here for the AND gates is considered as the 1, and for the OR gate it is assumed as the 0 on the basis of the truth table. So now here this is the table that represent that what are things are common, how we are going to get the 4 unique product terms is going to satisfy the both function. So last question is about the theoretical parts, that is about list and describe the different types of the ROM. And second part of this is the explain the internal structure of the RAM unit, discuss the decoding process used to select the specific memory word based on address. So first we'll see here about this different types of the ROM. Okay, so ROM already you know that we have mask ROM, programmable ROM, erasable ROM means it is the being erased with the help of UV lights, and PROM is the irreversible. Okay, and in case of mask ROM, path is provided for 0 and 1 as per the user's requirement. Next is the EEPROM. It is the electrically erasable. Okay, so during the working condition also you can erase the information. And flash memory you want means you can add this. Okay, so this is the faster. And internal structure means RAM, SRAM, how is the internal structures? Here we have latch, okay, and we have a word line, bit line, and it is connection is internal structure. In case of DRAM, we have MOSFET and capacitors, okay. So this capacitor is going to store the charge here. You know about the capacitor. So this is the internal structure about the RAM and ROM, and how for the particular address, how it is going to locate the word in the memory. So here one example is taken that if ROM size is 32 cross 8. So 32 cross 8 shows that it has 32 address location, means it will go to 0 to 31. Whereas it has word length of 8 bits. So second one represent the word length. So now this 32 information how we are going to get. So this 32 is to the power 5. So to the power 5 is 32. So here we are going to use the decoders. Decoder of the size 5 cross 32. So when 5 inputs will be given, it will generate the 32 unique combinations. So on the basis of that, each unique combination is going to represent the particular word location. So like this, from the given address, we are able to find the particular word in the memory. So these are the explanation. Now you can understand what are the mistakes we have done. Once quickly you go through this, okay? Even you feel you are right, you can see this video in little bit in fast speed, okay? Thank you. Thank you.